Right. So among the more brilliant ideas that I've had is recording this with like 7% battery life. So I'm gonna see if I can do this with one shot. But yeah, so welcome. This is first day of vibrations. Very first topic that we're covering is ODEs, or ordinary differential equations. Now, in the text, we have basically just a skim of chapter one, right? So, like what is a ODE? So an ODE is something that you're probably very familiar with. A very famous one is Newton's equation, F equals ma. Force equals mass times acceleration. Now, if you've ever taken a physics class, which you probably should have, you'd recognize that acceleration is also the derivative of velocity. So a differential version of this equation looks like this. dv over dt. It looks like a y. That's more of a t. Cool. So closer to something that you'll be dealing with is a second order ordinary differential equation, which you can express as dx squared and if I'll actually wake up for a day, there. All right. So this equation is kind of set up sort of like this. You have an independent variable. My bad. You have an independent variable. You have a dependent variable. And you basically have your derivative, or the thing that's changing. Can you tell I haven't gotten much sleep? So this derivative is basically the thing that's the differential part of this ordinary equation. So basically, anything that's not a constant can be expressed as a differential equation. What's really cool is you can take the momentum form of Newton's equation. So F equals... okay, backtrack a little bit. This whole thing is an operator. So a derivative is an operator of a function. It's not like an actual thing. And that's something that is very important. So you have to make sure to remember that to treat these as operators. This will come up a little bit further. But so this is a thing. And let's say your velocity is constant, but you have a constant or a changing mass, which is important for rocket equations. You can take this and it will still be a force. Isn't that cool? A changing mass times a velocity is a force. Who would have thought it? Apparently Newton did. Little sidebar here. Something that you'll be saying quite a bit is Euler's number, which is, E. And if you're familiar with the Markiplier meme, you'd be rolling in your grave right now. Well, not grave, but you'd be rolling in something. Maybe your bed or something like that. Anyway, E is the limit as 1 plus 1 over n times the nth power. Yeah, it's a cool little like fact that this number is derived from a limit as n approaches infinity here. So that is literally it from chapter 1. That is all that you need to know. First order, because it only has one derivative, and get over here. The second order. Easy enough. So chapter 2, we're going to start in 2.7, and this deals with homogeneous equations. I'm glad you can, this will give you a little bit of time to sip on your tea or whatever you're doing to enjoy this. You know, maybe relaxing in your chair right now, watching this video. So here we have like a general equation. Let's say we have the derivative of y with respect to x equals some function, right? Cool. Looks like a super simple equation. But there's no analytical solution for this. Try as you want. You will never be able to find an analytical solution to this. And an analytical solution is basically an equation that will satisfy this, or an integrated function that will satisfy this equation no matter what it is. So the simplest form of what's called a separable equation is this. It's the derivative of y with respect to x of the function y. There you go. It looks like the x formerly known as Twitter. Let's see, x. Cool. So you have two different functions multiplied by each other. This is a separable function because you can split it off and then take its integrals and do whatever you please with it. So here is where what I said about the derivative being an operator is more important than it being a fraction. So it does look like a fraction, and what I'm about to do is going to treat it like a fraction. But you need to keep in the back of your mind that this is not a fraction. So what we're going to do to solve this as an analytical solution is we're just going to integrate it. So I'm going to split this off. Times dx. Boom. This can be integrated as the function of, 1 over the function of h of y dy equals the integral of the function gx times dx. Cool. This has an analytical solution now. This has a function that is actually solvable. And this will turn out to be something like, what's a logarithm between friends? It's, ln of h y equals like gx plus c, right? Well, it's an antiderivative of gx, so it's more like, gx. And that c is extremely important. Don't ever forget it. With some of the examples you'll work, you'll definitely see that it's important. So the degree of a homogeneous equation, or homogeneous if you're British, is just basically this. Oh, this is important too. Forgot about this. Tx dy equals Tn f x y. Okay, cool. Here's your degree. And so you can say a homogeneous function if you basically factor out the degree. And the degree is pretty easy to recognize because it's the largest exponent. So the process for solving zero order homogeneous functions, very, very specific case. And it has to be a separable zeroth order homogeneous function. So you'll typically confront a ODE in this form. So it will be a function of m, x and y, dx plus n, let's see, x, y, dy equals 0. Cool, so you can split this up and actually write it like the typical function that we saw above, the whole, dy dx equals f of, that's supposed to be an f of xy. You can write this in that sort of form by doing this. Erasing a whole bunch of stuff and starting over. Because sometimes that's what you have to do in life. No. So it's f xy equals m xy over n xy. Maybe if I learned how to write, this would be a lot smoother. Cool. So since it's separable with 0, you can say from this thingy that, because this is an identity, so if you have a function of f of xy, which we have right here, this is equal to f of xy, and t to the 0th power, t to the 0th power is 1. So effectively, we can say that this equals f of tx ty. Let's see. So this is called a z substitution. And what you'll do is if this equation is true, then you can say that z is equal to y over x. And the t comes into play with, we'll also say that t is equal to 1 over x. And we can make this assertion that f of tx ty equals f of 1 y over x, which is then f of 1 z.